This video will explain how to use the Euclidean algorithm to compute the greatest common divisor of two numbers a and b. We will then use that work of the Euclidean algorithm to find integers x and y such that the GCD of a and b is ax plus by. We'll start with this example number 1, where a equals 270 and b equals 192. The idea with the Euclidean algorithm is we are repeatedly dividing two numbers over and over, getting their quotient and remainder. So our first step is to divide 270 by 192. We will keep up with this slightly different than just writing our division. We will say 270 is something times 192 plus a remainder. So 270 divided by 192, if we do that work, we ended up getting 1 with a remainder of 78. Now, the next step in the process is the 192 and the 78 move down and take the place of the 270 and the 192 before. So 192 equals some number times 78 plus a remainder. So 192 divided by 78, we end up with 2 remainder 36. And now we continue this process until we get a remainder of 0. When we get a remainder of 0, we can stop our algorithm. So we keep going. We'll move the 78 down, and we'll move the 36 down. Leave room for our quotient and remainder. 78 is 2 times 36, and then we have a remainder of 6. We keep going because our remainder is not yet 0. 36 is some number times 6 plus a remainder. 36 is 6 times 6 and a remainder of 0. That tells us to stop. Our algorithm stops when we get a remainder of 0. And then to find our GCD, we look for the last non-zero remainder, which in this case is 6. So what we have is that the GCD of 270 and 192 is 6. Now, for the second part of the problem, we're going to use the work we just did to find integers x and y so that the GCD can be expressed as ax plus by. What I'll do to start this is I always go to my second to last row where I found my GCD and I start there. So I'm going to rewrite it a little differently. I'm going to say 6 equals, so that's my GCD, right? GCD of 270 and 192 equals 6, which another way I can write 6 is I'm going to look over here and I'm just going to solve this equation for 6. I'm not going to do any multiplying out. Leave everything as is because we're going to combine like terms along the way. Remember, our goal is to figure out the x and y, and we want a and b to be in our original, a and b from our original to be part of our solution here. So 6 I can write as 178 minus 2 36s. So notice it's 78 minus the 2 times 36 would equal 6. Okay, it may seem strange that I'm doing that, but what I'm going to think about the whole way is I'm collecting these numbers, and eventually the 78 and the 36, I'll build them up to get here to my 270 and 192. So equals, now I can get rid of 36 because notice if I come up one step, 36 can be written as 192 minus 278. So this is 1 times 78, I'm going to leave that alone, minus 2 times, and now I'll replace the 36 with 192 minus 2 78. Now where did I get that from? 36 I replaced with 192 minus 2 times 78. Now I'm doing a little bit of combining of like terms, so 1 times 78. If I distribute this 2, I get minus 2 times 192, and then plus 4 times 78. Again, I'm never going to multiply these out because my goal is to backtrack through my Euclidean algorithm to eventually have my answer in terms of the A and the B, the 192 and the 270. So I can combine here. It looks like I have 5 78s because I have 1 and then 4. So 5 times 78 minus 2 times 192. All right, so that cleared out the 36. I can backtrack up and clear out a 78. So instead of 78, I can say 270. I'm looking at that top row of my Euclidean algorithm, minus 1 times 192. And then I still have this 2 times 192 left. Multiply that 5 over. I have 5 270s minus 5 192s minus 2 192, which, if I combine my like terms, 5 270s minus 7 192s. And notice what I've done. I'm back to my original A and B. I've backtracked all the way up through my Euclidean algorithm. And if you quick check with multiplication, 5 times 270, put in your calculator, then subtract 7 times 192, you do indeed get the 6 you were going for. Some patterns I want to just make sure you kind of see each time. I'm going to highlight some things over here on this algorithm. Notice here goes to here each time, and here goes to here each time. And you can kind of follow those patterns all the way through what's happening. Then we see, let me get a different color. You know, this 36 kind of goes through as well. So each number goes through and kind of cycles through on the Euclidean algorithm over there. And then over here on this right-hand side, when we're doing sort of the reverse version to get that linear combination, we see each time we're successively taking the smaller of the numbers and replacing it using its row over here. So I was able to replace, well, first of all, I started with 6, and it's 78 minus 2 times 36. Now I'll replace the smaller one. 36 is 192 minus 2 times 78. I'll clean everything up. Now 78 is the smaller one. I can replace 78 with the 270 minus 192 and clean it. All right, let's do another one of these. Got some larger numbers here, 4,567 and 91,837. Let's see what happens here. So remember, I start my Euclidean algorithm, do the bigger one, so 91837 equals some number times 4,567 plus a remainder. Okay, so if we do that division, we get that 91,837 divided by 4,567, it's going to be 20 with a remainder of 497. Oop, why did I write a 2? 497. And now I repeat my process. I move the 4,567 and the 497 down. So 4,567 is some number times 497 plus a remainder. When we do that division, we get 9, remainder 94. And we keep going. Remember, just repeat this process. So I have 497 equals some number times 94 plus a remainder. When we do that division, we'll get a 5, remainder 27. And we keep going, 94 equals some number times 27 plus a remainder. That's 3 times 27, and then we end up with a remainder of 13. Still not done. Remember, we can't quit until we get a remainder of 0. So 27 equals some number times 13 plus a remainder. 27 divided by 13 is a 2 with a remainder of 1. Still not 0, so I keep going. 13 equals some number times 1 with a remainder. All right, well, 13 is 13 times 1, and I get a remainder of 0. And I can stop there because I got that remainder of 0. Once you get your remainder, remember, just go up to the line right above it, and that gives you your GCD. Therefore, my GCD of 4,567 and 91,837 is equal to 1. Well, that's different than last time. If we have a GCD equals to 1, that means that these two numbers are relatively prime. They have no factors in common. All right, so now let's do the second part of our process. Let's rewrite these two numbers as some ax plus by. Let's figure out what that would be. Remember, always start at the bottom. So the GCD of these two numbers, 4,567 and 91,837, this equals 1. And if I start here at the bottom, 1 can be written using this row. So 1 is 127 minus 2/13. And then I'll get rid of the smaller one because I'm just going to go up one row, remember? So I need to get rid of that 13 with substitution. So 1 times 27 minus 2 times. And then 13 would be 1 times 94 minus 3 times 27. And I'll do a little cleaning. So that's 1 times 27 minus 2 94s plus 6 times 27. Just distributing there. So I have 7 27s minus 2 times 94. Okay, I'm going to move up. Which one of these is smaller? Smaller is the 27. I'm going to go up here and replace the 27 with 497 minus 5 times 94. So 27, I have 7 times 1 times 497 minus 5 times 94. And I still have those two 94s hanging out on the end. Okay. Distribute, I have 7 497s minus 35 94s when I distribute, minus the 2 times 94. I can combine some like terms. I have 7 497s, but now I have negative 37 94s. Okay. So now looking at these two, I'll move up 1 to my 94 row. So I have 7 497s minus 37, and I can rewrite 94 as 4,567 minus 9 times 497. So clean this up a little bit. So that's 37 4,567s plus the 37 times 9, which will be 333 497s. And combining like terms, I see the 7 of these here and 333 of them there. So I have 340 497s minus 37 4,567s. Okay, I'm almost done. I see that 97 is my smaller of the two, so I move up here to this top row. So this will be my last substitution because I'm back to my top row and I'll have my original A and B now. So this is 340. 497 is 91,837 minus 20 of the 4,567s. And then I still have 37 left on the end. All right, I'm going to need to do some distributing to clean this up. I'm going to scroll up some. This is 340 times 91,837 minus 20 times 340 is going to be 6,800. Oops, 6,800 of these 4,567s, and then I still have these 37 on the end. And if I combine like terms, I have 340 of the 91,837s, and I take away 6,837 of these 4,567s. So my originals were the 91,837 and the 4,567. So I have figured out a way to write my GCD, which remember, scroll back up, this was all equal to 1. 1 is 340 times 91,837 minus 6,837 times 4,567. And that is how I can write that.